So today we have one of our faculty, Mustafa, is going to talk about interpreting data science as using Python. And so basically, he's going to talk about statistics with Python. It's really good informative program. So he has a material engineering background, and he has also a master's degree in management. And he's almost finishing the PhD in economics. He's been working on several projects with Magnimind on NLP. So, and we have also collaboration together with Stanford and Mustafa working on it as well. So I hope you guys like today's program. If you have any questions to me about the programs and Magnimind overall, you can either share your thoughts with me or at info@magnimindacademy.com. So, Mustafa, it's now yours.
Hello, everybody. Let me share my screen first. Okay, back to meeting. Just a moment. Okay, I hope you see the presentation. My name is Mustafa Yucel. I usually use Mustafa Ray in LinkedIn as a convenience for the English speakers, native English speakers. As Murat said, I'm doing projects in Magnimind, mostly on NLP. Today we will talk about interpreting data using descriptive statistics with Python. First of all, let me express my opinion. Probably you have a good knowledge about statistics or prior knowledge about statistics. Today, I'm not thinking I will give something really important. These are simple subjects, but what I want to talk or express today is when I talk people about statistics, I understand if they took statistics in university, most of them hate statistics. So this is a data in my hand. So this is the, I mean, this is data is true, but the meaning is not that true. I mean, statistics is not that difficult or not that ugly, but almost everybody I talk to don't like statistics or those kind of things. So today the subject is simple, but I want to uncover the beauty or uncover the beauty of statistics or easiness of the statistics. So let's start. First of all, we will have a presentation, but at the end we also have a Jupyter Notebook presentation about what we talk in the first presentation. So today in the world, you know, we are covered with a lot of data. But even, I mean, everybody is full of data. First of all, we have to understand what those data tell us. Today, we will talk about descriptive statistics is used to explore and describe measures of central tendency. And then we will talk about measures of dispersion, the Gaussian distribution, z-scores, confidence intervals of measure, and bivariate measures such as covariance and correlation. I think you have knowledge about those things, but we will talk and then we will go through our Python notebook. as I said, we will try to understand the descriptive statistics, and then we will working with descriptive statistics using pandas. Statistics in understanding data. As you know, we are dealing with data everywhere, and then there are two divisions of statistics. These are descriptive statistics, which we will talk today, and then the other one is the inferential statistics. In descriptive statistics, we identify important elements in a data set. In inferential statistics, we explain those elements via relationship with other elements. This is a little more advanced than the descriptive statistics, but descriptive statistics is still very important in understanding your data. Here, we will see a little more detail. In descriptive statistics, we will deal with univariate, bivariate, and multivariate descriptions or points of view of data. In inferential statistics, we will deal with hypothesis testing and model fitting, which we will not cover today. And then here we will start with key terms for data types. If we deal with data, first of all, we need to understand what are the types of data. These are simply in two categories: numeric data types and categorical data types. When we say numeric, those are data that are expressed on a numeric scale, and then these are two categories: continuous and discrete data. When we say continuous, those are data that can take on any value in an interval. Those can be said interval or float or numeric data. When we say discrete, we can say data that can take only integer values such as counts, number of people, number of cars, something like that. These are integer or count. When we deal with categorical data, which is a very important part of the statistics and also in advanced part of the study, it's an important part of the machine learning. Categorical data that can take only a specific set of values representing a set of possible categories. These are also called nominal values in different books, but let's say, or in statistics, they say nominal, but in data science, they mostly say categorical data. These are also can be expressed as binary data. As you know, binary data just has only two set of values, true, false, 1, 0, and these are mostly logical or Boolean expressions. Ordinal data is also categorical data, but it has an explicit ordering. Let's say, first of all, when we say colors, blue, red, or green color are all the categories which are equal importance. We don't say blue is important than green. But when we have ordinal data, those are again categorical data, but they have orders. When you look at the reviews, and let's say on the marketplaces, reviews are, let's say, 5-star, 4-star, or 1-star reviews. Those are a kind of ordinal data. And then here, descriptive statistics, we will summarize data as it is. We don't posit any hypothesis about data. We do not try to fit models to data. We try to understand what data tell us. We don't produce hypotheses and then models. It's a very important initial step in data analysis. We shouldn't omit this step. It's a bad sign of data analysis. It enables you better understand your data. Let's say you have a new data set. For sure, the first step is you load your data and then you try to understand data before you produce anything. What data tells you? What are the features? Are they categorical or numeric, continuous? We check everything, and then We detect outliers also, we will talk about it. This enables you to do feature engineering as well. When you do analysis or when you check descriptive statistics, you will see your data, you will see your features, and then you may produce new features from your data. Related subjects are exploratory data analysis, which I just expressed. And the second is the explanatory or descriptive visualization part. This is, again, as expressed, about the visualization. The visualization is also a very important part of the analysis. Sometimes just one visualization is more than talking and half an hour, something like that. You see the reality in your visualization or in one graph. So we do both exploratory data analysis and explanatory data or visualization. Today we will do both. When we say descriptive statistics, we will deal with univariate, bivariate, and multivariate statistics. Here in univariate, we will see, or we will check first, frequency, central tendency, and dispersion. I'm sorry, just I will take over. Yes, we will talk about frequency and central tendency and dispersion of data. Measures of frequency, the first one is the histogram. Histogram is something probably you know very well. Histogram is something like on the left. This is a distribution of our data. Most well-known form of this one is the students' grades. I guess everybody is a graduate of a university. So in university, you encountered this diagram a lot, or you know this very well. This is a distribution of the grades, let's say, in your class. In the class, most of the students are in the center of the grades, but few students are top or around the top, few students are bottom or around the bottom, but most of the students are around the average, a little more than average, a little less than average, but most of them, sometimes 60%, 50% are around the average. And then here we will see the distribution or the frequency of the data. The grades are just one very simple example. We will talk also about the income distribution. When you check, let's say, income distribution in your community or wherever you live, you will see something like this most of the time. We will talk about, let's say, skewness. There are some skewed data, right skewed, left skewed. In those kind of data, okay, everybody is around the center, but some part is really longer than the other side. Let's say in some data, the right tail is longer, in some data, long tail is longer. This is skewed data. This is the first part. This is the histogram. And then we will talk about also average, median, and mode. Yes, here mean is the average, the most popular and best understood measure of central tendency for a quantitative data, not suitable for categorical data, a single numerical calculated value to represent data. Every data points are considered in calculation. Outliers, I mean very big or very small values, are the disadvantage of this method. Outlier means an extreme data point, unacceptably far from the mean. Here, the logic is simple. Mean, everybody knows it's the average. You sum up all data points and then you divide the number of data points and then you get the mean. But although it's very simple, in my understanding, this is the base of the statistics. let's say when you go advanced part of the statistics and machine learning, even in deep learning, you will see this measure mean in everywhere. And almost everything is based on mean. And then everything is produced, even machine learning and deep learning is produced how data points are far from the mean. In this simplest form, it's mean. But let's say in some advanced forms, it will be a line. In regression, it will be a line. How far data points are from the line. In, let's say, 3 dimensions, it will not be mean or a line. It will be a kind of plane. How far our data points are from the plane. As simple human beings, we can just visualize 3 dimensions. If data has more than 3 dimensions, let's say 10 dimensions, in some cases 100 or 1,000 dimensions, or in NLP, natural language processing, you can have 100,000 dimensions, let's say. In those cases, we cannot visualize or we cannot see the plane. In that case, that's not the plane, that's the hyperplane, in fact. In that case, we calculate how far are data points from the hyperplane. So mean is simple, very basic, but almost everything is based on the mean. Even in advanced area, mean becomes the line or plane or hyperplane, and we calculate the residuals of the data points. Here you see a very simple example. On the left, this is the mathematical expression. We sum up everything, and when we divide with the number of data points here, our data, and then another important thing is, let's say, when we calculate our mean, and then when we subtract data points from our mean, and then we sum up the residuals, the sum of residuals is always 0 in mean. This is what we get at the end. Mathematically, you calculate mean, and then when you subtract all data points from the mean, you measure how distant are data points from the mean, and then when you sum up those residuals, they always give you 0. Another simple example for mean, these are our data, and then when we calculate the mean, we sum up and then we divide the number of data points, and then we get 75. I'm using this for some median understanding in other slides. Outliers are some extreme data points. Here, it's even not very extreme data point, but when you think, let's say, okay, I will talk a few minutes later. This is a kind of outlier, and then when we calculate the mean, here just we edit an outlier, and then we divide the total number of points, and then we get 207. This is much bigger than our original mean 75. It shouldn't affect this much, but this is the weak point of the mean. When you have outlier, the mean is affected too much. Median is a little more robust, not a little, it's really robust. When we calculate mean, the value such that 1/2 of data lies above and below. It's the 50th percentile in another term. We will talk about it. First of all, we sort data from the biggest to lowest, or the smallest to the biggest, and then we take the middle data point. That is the middle element is the mean. Because of this, we just take only middle data point. We don't look at the 2 big data points extremely slow, extremely small, extremely big. We don't look at them, we don't calculate them, we just sort and then we take the median. And then median in that case is very robust to the extreme values. Here we will see, just a moment, if data has even number of elements, medium lies between middle two elements. These are different, there are different methods for calculations, but you can simply consider average of those elements. Let's say when you have odd numbers, let's say 11 data points, so you can put 5 above and then 5 below, and then the one is the middle. You can take the middle as the median. But when you have even numbers, 10 numbers or 10 data points, in that case, you have two middle point data points, not one. In that case, you take the average of these data points. There are different calculations methods, but for simplicity today, we will take the average of those two elements. It's robust. And then here another simple example. And then first of all, we order data from smaller to bigger one. And then, as you see, there are two data points, not only single one. If it was a single data point, we will take it. But here there are two, and then we will take the average of those two data points, and the median is 75 again. Impact of outliers, the same data, just one additional outlier. Here we order data again, and then you see new median is the 80, and then it's not very far from 75. But in case of medium, it's affected too much. There is another funny example. Let's say in a room, you are in a meeting, and then in that meeting, there are 100 people. And then they said, okay, we will make a survey, and then we will calculate the average or mean income of this group, 100 people. And then you calculated average salary or average income in your meeting. But if you add Jeff Bezos to your meeting, just one single, how to say, outlier in 100 people, and then when you calculate the mean, you can think everybody in the room is a millionaire. But it's wrong. When you get the median, one outlier doesn't affect. The median is still somewhere in the center. Mode mostly used for categorical data, the value or values that appears most often in dataset. In case of histogram, it is the highest bar, the category with highest number of elements. It's another simple example. Let's say you are in a car park, and then you counted the cars, and then these are the numbers of cars. Civic, Sonata, Avalon, Audi, Fusion, and Golf. When you look at the mode is the most frequent element in the dataset. Here in this dataset, Civic is the mode, or mode is Civic and 9 in this dataset. In some data sets, mode is not only one single value. Let's say if you have the same numbers, Civic and Sonata, in that case, you have two modes in your data set. I'm sorry. Here now, for univariate descriptive statistics, we have already seen histogram. As you remember, the students' grades or income histograms, mean, median, mode as measures of central tendency. We are looking for the center, a kind of center of the data. And then now we will see measures of dispersion, range, maximum, minimum, interquartile range, standard deviation, and variance. estimates of variability. When we say measures of dispersion, this is a kind of variability. When you have a data set, we check how variable your data is. Let's say you have, let's say in university, there are two different classes. When you look at the grades, if they are too much different in the same class, that there is too much dispersion or variability. But when you see the grades are similar to each other, not very far from each other, in that case, the variability or dispersion is less. There are different measures for this. This is another sample from drug industry. As you know, these days, drugs or medicine and vaccines are very important things. Here, let's say there are two drugs, drug A and drug B, and these are the drug response times. You see in this drug A, response times are, let's say, different. It's not centered here. But when you look at the drug B, mean, median, mode is the same, and it is not very dispersed. Okay, there are still some minimum and maximum values, but most of the data are centered here. Here, it's not centered, it's dispersed. Measures of variability. If you examine the two histograms, you will notice that both data sets are symmetric with equal modes, medians, and means. However, drug A has response times spread with almost equal relative frequency over the measurement classes. I already talked about it. Consequently, you can see that we need a measure of variability as well as measure of central tendency to describe a data set. Let's say with another example, let's talk about a basketball team. In the basketball team, you can measure the average height of the team, and then you see an average. You can take another basketball team, and then you measure, you can get the same average height. So you can think these are similar teams, but when you check dispersion, you can measure, let's say team A has, let's say it's not very centered. You can see short players, very tall players, but in the team, second team, you can see in detail, most of the players are just around the central data, yes, around the average. It's not very dispersed. It's another measure is the range. Here range is very simple. We calculate the maximum of the data set and minimum of the data set. When we subtract the minimum from the maximum, we get the range. Let's say in your university class, the highest grade is 100, but the bottom is 20. In that case, the range is 80. You subtract minimum from the maximum. But in other class, let's say the maximum is 90 and minimum is 70, the range is just 20. The measure between maximum and minimum is just 20. It's not very dispersed. Quantiles and interquartile range. These are another measure of dispersion. When you sort your data from smallest to the highest, let's say you work in a company and then you sorted your salaries, everybody's salaries from smallest or to the highest, or lowest salary to the highest salary. And then when you count those, let's say the lowest 25% salary, that's the first quantile. The first quantile always has the 25% lowest salary. When you add 25% higher salaries, then you get second quantile or the 50% quantile. if you add 25% more higher salaries, then you get the third quantile, and then the remaining 25% is added, and then you get the 100%. That's the maximum value of data point. Here, what's important, first quantile and third quantile is important for us. In some calculations, we want to see what's the interquartile range. That means the range between third quantile and the first quantile. We want to measure this 50%. Our 50% data lies here in this interquartile range. So it's important, this interquartile range, just we subtract the lowest 25% and the highest 25%. We just measure the data points around the average. Here, box plots are used for this kind of not calculations or visualizations. When we plot box plots, as you see, these whiskers represent the minimum and maximum in our calculations. It's not the maximum point, but in our calculations, first of all, this is the minimum point, and then we get the first quantile, and then this is the median or the 50th quantile. This is the third quantile, and then, in fact, maximum point is here, but these are some extreme points, and we have to show these extreme points. So we calculate a kind of fourth quantile here. There are different calculations, but it's generally accepted that when you calculate this interquartile range, and then you add 1.5 times this range here, and then you get the fourth quantile here. Above this point, these are the extreme points, and then these are called as the outliers. So first we measure interquartile range, 75% and 25%. We measure this distance, and then we add 1.5 times this distance here, and then we get this the whisker. They say whisker here. Above this whisker, these are some extreme points. In some cases, those extreme cases are not there, but here in below the lower whisker, those are again some extreme points. Okay, by the way, I made a mistake. I said we start from the minimum. No, we don't start from minimum. In fact, we start from the median. Anyway, here, anatomy of box plots to understand. You see, this is the lower whisker, this is the higher or maximum whisker. There are points out of these whiskers. In this case, it's here, but sometimes it's here. And then first quantile and third quantile. The median is always between these, sometime close to first quantile, sometime close to third quantile, but always between these. And then these are all data points. These are the extreme ones. Okay, this is the calculation of whiskers. As I said, whiskers, first of all, we calculate the interquartile range, and then we multiply with 1.5 dot with that interquartile range. Below and above the whiskers, data points are the extreme data points. Okay, median is always second quantile. Second quantile is here. That's always median. Variance is another measure of dispersion. It's widely used, or it's a way of reaching to standard deviation. In fact, variance is calculated. Both samples have here there are two samples. There are data points, and these are the averages in samples. This is sample 1 and sample 2. But you see in sample 2, data points are close to each other. Here they are dispersed. Both samples have mean of 3. If deviation is large in magnitude, as in sample 1 here, the data are spread out or highly variable. In case of, let's say, you can think about a basketball team. There are very tall players and short players, and they are dispersed. Here, let's say, in this case, most of them are around the average. If the deviations are mostly small, as in sample 2, the data are clustered around the mean, therefore do not exhibit much variability. Here is the mathematical formula or variance. In case of variance, it is S square. We calculate, first of all, mean again. Mean is the base of statistics in my understanding. First of all, we calculate mean, and then we subtract mean from each data point. Or you can reverse, it's not very important. As you remember, in our mean calculations, when we subtracted the average from data points, at the end, when we sum up these like this, we get 0. So this is a problem in calculations. When we get 0, we cannot calculate dispersion from the 0, because mean is average. Some points are bigger than the average, some points are less than average. When you subtract them, some of them are positive, some of them are negative, and then when you sum up, they are 0. In order to avoid this, we subtract average from data points, but we get the square in order to avoid minus or negative data points. In that case, when you get the square, square is always positive. And then we divide this n minus 1. Don't worry about this illustration. It's a kind of calculation. Here, you know this when you calculate the average. The square is just to get rid of negative values. Here, we will talk more about this. When standard deviation is produced from the variance, but the problem is in, let's say, variance, when we have, let's say, data in kilogram, when we take the squares of kilogram or pounds, it becomes pound square or mile square or dollar square or something like that. Squared data is difficult to understand or to get a picture from the squared data. In order to avoid this, at the end, we take square root of the variance. This gives us a value in the same measurement. Let's say if your data is height, let's say in meters, then standard deviation is again in meters. If it is income in dollars, the standard deviation will become in dollars. So you will get an understanding, or you will get the picture how dispersed is your data. The standard deviation is a measure of dispersion. When your data is dispersed, standard deviation is bigger. When points are close to each other, or they are clustered around the average, in that case, we say the standard deviation is smaller and data is not very dispersed. It's a very useful measure of dispersion. As you remember, we already talked about range. In range, we just subtract minimum from the maximum. It's a kind of, okay, dispersion value. We calculated interquartile range. That's okay, a good method. But this is another method. We look at variance, and most importantly, we look at the standard deviation. Here, Gaussian normal distribution, we will use that value the standard deviation in this Gaussian normal distribution. It's a probability distribution. It tells you how likely a value to occur in your data. Just a moment. This curve is bell-shaped curve. I guess you are very familiar with this curve. It's a probability distribution. Here, this is the average of data points. This is the maximum, minimum. You can have some extreme values here. And then there are calculations, but we will not talk about calculations today. This is a very common distribution, bell-shaped curve or normal distribution. Most of the data points are around the average. Here you will see another distribution. In this distribution, let's say it's like tossing a dice. You have a dice and getting 1, 2, 3, 4, 5, or 6 has the same probability. Getting 1 probability is 1/6. Getting 3 is 1/6, or getting 6 in your dice is 1/6. All probabilities are equal. But here in this case, getting something similar to average is highly probable, but getting an extremely large number or extremely small number is less likely. So this is a normal distribution. In real life, properties are normally distributed in most cases, not every cases. Grades of students in a class, incomes of people in a society, errors in products in a production line are distributed normally. Okay, here we see the average and then we see the standard deviation. When we have average and standard deviation, we can draw our Gaussian distribution with these two values. This is the formula, but today we will not deal with this formula. You don't need to memorize this formula. We just talk about this is the distribution, and then data points around the average are mostly probable. These are less probable. Small and big values are less probable. Here, what's important here, we can draw two lines in this shape, and then this is one standard deviation bigger than average, and then one standard deviation smaller than average. This area is very important, and this is most of data points are here. I think the next slide shows the real value. If it is normally distributed data, the 68% your data lies in this range. This range is calculated. You subtract standard deviation from the average, and then you add standard deviation to the average. This area has the most of your data points. 68 data points are here. They are clustered around the mean. Here, extreme values lies in the vicinity of the tails. Okay, this is one standard deviation of mean. 68 data points are within the one standard deviation of the mean. We will see one more case here. This is the two standard deviation of means. Standard deviation is here. If we go two standard deviation to the lower point and then two standard deviation to the higher points, in this area we will have 95% of our data points. If we add one more standard deviation, in that case 99% data points are within 3 standard deviation of the means. You will get almost all of your data in 3% standard deviation. So as you see, it's very important to calculate your standard deviation. And it's very important to get to the point when you are far from the standard deviation, or when you are far from the, let's say, average, you start becoming an extreme data point. If you are far from the average, let's say if you are 3 standard deviation far from the mean, then in that case, you are really an extreme value here or here. If you are bigger than the 3, let's say, if you are 3 standard deviation bigger than the mean, then you are an extreme point, and here or there. Here I want to talk about, again, these scores. When you describe your data, when you calculate your standard deviation, you can also calculate the z-scores. Let's say this is the grades of students, and then the average is 70. The average of the class is 70, and standard deviation is 10. In that case, let's say when we get a student and then his or her grade is 80, in that case, since this is just one standard deviation from the average, it is z-score is +1. If, let's say, average is 70, but a student is here, and then it is, let's say, 65 point. If it is 65 and average is 70, and then our standard deviation is 10. So the student's distance to the average is 15, but standard deviation is 10. In that case, its z-score is -1.5. It's 1.5 standard deviation far from the mean. So these scores are calculated and used to understand each separate data point, how far a singular data from the mean. Let's say you will choose a school for your child, your kid, and then you check the let's say averages of, let's say, how to say, chemistry class averages of schools around your home, and then you made a calculation, you look at the average of the schools, and then you calculated z-scores of the schools, and then you find out a school z-score is -3. That means that school is very far from the average, and it's in the negative direction. You have to take, you have to consider twice before you send your children to that school. But let's say you find a school and school's z-score, let's say +2. That means it's very good school, or very it's deviate from the average in the positive direction, and it's 2 is really good. Roles of sigma and mean. Here we see the average values. This is 40 and then 10 and -10. These are okay, but when we look at the standard deviation, if standard deviation in this case, let's say smaller, then that means all data points are clustered around the mean. When it becomes bigger, the data starts spreading from the mean. When it's bigger, you can find really data points far from the average in the positive or the negative directions. Skewness is a kind of deviation from the Gaussian distribution. In this case, in this data, this is right scoop data. In here, it's left scoop data. That means here there are some extreme points out. Let's say you calculate your standard deviation. These are really far from the, let's say, positive 3 or 3 negative 3 standard deviation. These points are far from the 3 standard deviation. Here in that case, these are in the negative side. When you calculate the average, these data points probably far from 3 standard deviation, and it's in the negative direction. You can find some examples. Let's say if it is basketball player or basketball team heights, in this team there are really tall players. In this team, okay, most players are here. You can find really some short players. Confidence intervals here. Sample to population. Population, we didn't talk about much. If you have the opportunity to reach all data points, real data points, that's the population. Population includes all data points. Population has parameters, sometimes called population statistics. Let's say if you want to calculate ages of people in the Bay Area, the population is the all Bay Area people. In that case, it's almost difficult to reach everybody in the Bay Area. So in most cases, you cannot reach the population. In that case, we take samples from the population. Sample is considered as a representative of the population. We will not talk about sampling methods, but somehow we have to sustain randomness of the sample. When we have a sample, we have sample statistics. Here in population, we have population parameters, or population statistics. Here we have sample statistics. In sample statistic, again, we have average, but this is sample average. And then variance is also calculated for the sample. Estimating population mean, we need to estimate a statistical property mean of the population. Let's say we are not able to reach everybody in the population. When I say everybody, okay, in Bay Area case, it's real people, but in some cases, it's sometimes the measurements of error or production error or all kind of statistics. It's not have to be people. So we need to do this form of sample, and then we use properties of sample to estimate property of population. If we are not able to reach everybody in the Bay Area, we get a sample from the population. And then there is sampling distribution. It's probability distribution of population statistics. In our case, it's the mean given a particular sample. Let's say we want to find the ages of or the average age in the Bay Area. So we are not able to reach everybody in the Bay Area. We get the statistics, or we get a sample, and then we measure the sample statistics, or we produce the sample statistics from the sample. We can get 1,000 people or 5,000 people randomly, and then we measure we measure the average, and then from that average, from the sample average, we try to estimate the population average. Here, it's a good illustration. This is the real data. Let's say this is the Bay Area ages. Okay, here there are really older people in our sample. Let's say just as a sample. Here we have, let's say, samples, and then when we plot these samples, and then the sample, let's say, samples are smaller or bigger. When, let's say, when your sample size smaller, you can still see some deviation from the average, but when you have some bigger samples, in that case, you will see the averages just cluster in around some value. Here in real data, we don't know the real average is. We cannot see this graph in real life, but we try to estimate from our samples. If we have really big sample sizes and then we plot their averages, or if we draw their graph, something like this, in that case, let me see here. In that case, we will see the data averages or sample averages cluster around here, and then we estimate our real data average from this sampling distribution. Let me see here. What's the property of Gaussian distribution that makes it occur so often in nature? Okay, what's the property of Gaussian distribution that makes it occur so often in nature? I'm not sure. I'm not sure why it's so. Because in nature, let's say, in my understanding, it's not something scientific. Extreme values are not very common in nature. Most of the individuals are somehow around the average. The individuals far from the average are not that common. So we see, in my understanding, this kind of distributions in nature so common. Okay. Okay, key terms for sampling distribution. Sample statistic, a metric calculated for sample of data drawn from a larger population. Data distribution, the frequency distribution of individual values in data set. Data distribution is the here, just a moment. This is the data distribution. This is not sampling distribution. These are real individuals. But sampling distribution is different. Frequency distribution of a sample statistic over many samples or resamples. Here again, these are not real individuals. These are group of individuals. And then we take, let's say, 100 groups and then samples, I mean, and then samples has some definite size, and then we measure their average, and then we draw this graph. This is another sampling distribution with some bigger sample sizes. Here sample sizes are smaller, here sample sizes are bigger. When you go bigger sample sizes, graph becomes steep, and then clustering becomes more visible here. This gives you more robust estimation for the real data points, real individuals. Central limit theorem, the tendency of sampling distribution to take a normal shapes as sample size rises. Yes, this is to say, when you take samples and then when sample sizes becomes bigger, this graph becomes steeper and more robust. It is something like that. And standard error, you know, the standard deviation. Here we have standard error, the variability or standard deviation of sample statistics over many samples, not to be confused with standard deviation. which by itself refers to variability of individual data values. Here again, just a more. Here again, this is real individuals. We plot their graph, and then here we have a real average and then real standard deviation. But when we go to the sampling distribution, we have many samples. From many samples, we reach this distribution. In this distribution, since these are not individuals, these are groups or these are samples, we don't say standard deviation. Here, we just say standard error. It's the same calculation, somehow similar calculation, similar meaning, but here in real data points, real individuals, it's the standard deviation. But in sampling distribution, you have lots of samples and then you draw this graph. Here in this graph, you calculate the standard error. It's similar to the standard deviation. Okay, it's the same thing. When you do those calculations, 6 to 8 point confidence, that's the mu is within the first standard deviation of X. Okay. I'm a little, my voice is a little, sorry. Here, these are the calculation side of these things. I really don't want to talk too much here, but as a just general understanding, we already know that if it is normal distribution, 98% of data are here again in the first standard deviation. In case of sampling distribution, the calculation is a little different, but it's the same meaning. Here, okay. Okay. Confidence intervals. Confidence intervals are the typical way to present estimates as an interval range. Let's say you estimate your real data mean average from your sampling distribution, and then in that case you have some confidence intervals. You are estimating, you are not 100% sure because you don't know everybody in the population. You have just sampling distribution. From this sampling distribution, you estimate the mean or average of the real population, but you give yourself a confidence interval, how confident you are. We say how confident you are in your estimation. In that case, if you have really big samples, if sample size is big, in that case, you are more confident in your estimation. If sample sizes are smaller, in that case, you still estimate the average of your population, but in that case, since your sample is smaller, sample sizes are smaller, in that case, your confidence interval becomes a little bigger. The lower the level of confidence you tolerate, the narrower the confidence interval will be. If you want the lower the level of confidence you can tolerate, the narrower the confidence interval will be. As I said, if let's say you want to be confident, really confident about your estimation, in that case, you need to get bigger sample sizes in order to estimate with more confidence. It's something like this. Here's some questions. I think there is a question about here. Where was the question? I think the question is about this. Okay, we are trying to estimate the real population. Why do we divide this square root of n? As I said, if you have, this is the sample size. When you have bigger sample sizes, this is the denominator. As you see, the mean is here. The mean of the sampling is here. It's here. But when you have bigger sample sizes, now we will put a plus confidence here. If you have bigger sample sizes, this means this is the denominator. The interval will be smaller. You see, this is denominator. The average is here, but if you put some confidence here, when you have big number in the denominator, the confidence will be, or confidence interval will be confined here. When you have smaller samples, in that case, this number will be bigger, and at the end, you will have a wide confidence interval. We want to be confident as much as possible. In that case, if we increase these sample sizes, we will be more confident in our calculations. It's about the sample sizes. I didn't go through the calculations too much. I just said the rough idea about sampling. If you need really good estimation, or if you want to be confident, we need to increase the sample sizes. Smaller sample sizes gives you a big confidence interval. Let's say, think about the, okay, elections. In the elections, they say, okay, they make a prediction, and then they say plus minus something. If you want that plus minus smaller, then in that case, you need some bigger sample sizes. It's something like that. Okay, now I will share another, just a moment. I will share another screen. Okay. I hope we have enough time. Okay, do you see the Jupyter Notebook in your screen? Yes. Okay, here I tried to prepare a notebook about what I discussed in the presentation. Let's try here. First, I imported, by the way, I assume you have the prior knowledge or a knowledge of Python, and you are somehow familiar with NumPy, Pandas, Matplotlib, and Seaborn libraries. Okay. First of all, I need to generate some data to express what I discussed in the presentation. So we assume 3 companies, each of which has 1,000 employees. We will discuss here 3 different companies with 1,000 employees, and then we will generate random salaries for these employees, and then we will arrange data in a way that it will show Gaussian distribution. I mean, we will generate, but it will show Gaussian distribution. And then the salaries for each company will have different means and standard deviations. Here, I fix the seed to a certain number, because otherwise, if you don't fix it here, every time you run the notebook, you get some different values. In order to avoid this, we fix it 0. You can fix it any number. It's not very important. And employees are 1,000. These are the salaries or average of salaries of 3 companies. And then these are the sigma, that is the standard deviations of the companies. Let's say in the first company, the average salary is 70,000 or 70K, and standard deviation is 15. The second company, salary and standard deviation. The third company is, let's say the salaries are higher. This is the average salary, and this is the standard deviation. That means in this company, the salaries are really spread. You can find really very high values and very low values. In this, salaries are, let's say, less than this one, but also the spread, dispersion is really less than this one. In this company, the salaries are really dispersed. Here we generate our salaries, and then we put them here, and then these are our data, generated data, and we sort them from the smaller to the biggest. This is the lowest salaries in those companies. These are the lowest salaries, and these are the highest salaries in this company. Let's say the lowest salary is 9,000, an imaginary salary, okay, and the highest salary is the 281K per year. And then we put this in a data frame, and then we transpose it in order to see something like this. In columns, we give them the names, company ABC, and then we get our salaries data frame. This is the head of data frame. That means these are the lowest salaries because we sorted them from smallest to the biggest. These are the lowest salaries in company A, company B, and company C. As you see in company C, the average is very high, but since the dispersion is too much, you see the lowest salary in this company is even less than this company. In this company, the average is 70. When we look at the tail here, tail means the highest salaries in this company, 111K, in this company 281K, and the shape of the companies are, or the salaries are, we have 3 companies, and for each company we have 1,000 individuals. Just to show you, to check if there is any NaN or null values. There is no null values. Here we will see exploratory data analysis for univariate variables. We already discussed about the histograms. Histograms are the dispersion of data points. Here we will use the pandas built-in methods. Later we use also Seaborn or Matplotlib, but here pandas built-in methods really works well. Data frame, just data frame, and hist means histogram. We write the figure size. Alpha is the density of the color. You produce histogram of company A, B, and C. You see these are produced manufactured data, but you see this company has really, the average is around 70K, and this is around, I think, 20K, 120K. This is something around 150K. Dispersion is here. Then we will check box plots. We already have seen box plots. Data frame plot, again we use pandas built-in methods. Data frame plot box, figure size, and then it will give us the first company, second, and third company. You see in this company, most salaries are clustered around here because our standard deviation is very small here, just it's 15K. It's around here, but there are still some extreme values above and below the whiskers. This is here in this company. Most salaries are here. This, you know, the first quantile, second quantile, third quantile. Most of the data are clustered here, but still there are some extreme values. And this is the third company. You see it's really spread. Okay, many of the people here, but you see there are some still extreme points. The plot is very simple, data frame plot box by using pandas built-in methods. Here we use Seaborn library. Seaborn is a high-level library built on the Matplotlib. In Matplotlib, it's low-level. It's not very important, but Seaborn is more easy to use or flexible for statistical visualizations. We already did here plot here, but with Seaborn, we are doing something like this, and then SNS is the Seaborn box plot. Data is data frame, and we palette is the color. When you, okay, it's set to, but when you put set one here, you get another color for data. But the same, everything is the same plot, the meaning is the same, the palette is just the visualization. Central tendency mean is calculated easily. Data frame mean, okay. I just rounded to 1 digit because otherwise it gives a little detail. We don't need them. We can even round to 0. These are the means. Pandas can calculate every company mean very easily. Here we see the individual company statistics by means of data mean, data frame mean, but we select, let's say, the first company here. Here, when you select the first one from the data frame, it gives you this one, or from the series, not data frame. This is in fact a series. Calculated means close to intended means, question mark. These are the means we calculated, but at the end, but at the beginning we produced data and then we intended something. So we will look at this one. First of all, we produce calculated mean data frame, and then we add intended mean. This is the mu. Mu is the initial array of means. These are the intended ones. We intended 70K, 120K, and 150K. But when we calculate, our data is something like this, very similar to our intention. But here in company C, maybe because of the dispersion, it's a little deviated from what we intended at the beginning. Median, okay, when you have data frame and median is calculated very easily. These are the medians of the salaries, company A, B, C. Mode, again, data frame mode. It's something like this. Just I transpose. If you remove the transpose, you will get something like this. It's not very important, but usually I prefer transpose. It gives a better understanding for me. So how close mean and median to each other? Okay, we calculated mean and median is here. When we put them in the same data frame to show differences or the similarities, okay, these are the medians. These are real values. When we sort from the smaller to bigger, we get these individuals. This is an individual, this is another individual, this is another individual, but these are the calculations. Mean are calculated. You sum up every individual and then we divide them. You see, since our manufactured data, produced data is, let's say, Gaussian distribution data, our mean is similar to a median. Let's say there is no too much extreme values. If there was some extreme values, the mean would deviate from the median, which is not the case in our case. Measures of dispersion, we have DF, with just one max, we can calculate all maximum values in our data frame. These are the maximum salaries in those companies. Data frame minimum, you can get all minimum salaries in those companies. Range, range is the maximum salary minus minimum salary. So we already produced company maximum and company minimum data frame. When we subtract maximum and minimum and put a new data frame, it's here or in a new series, let's say. These are the range. In this company, the difference between maximum and minimum salary is something like this. We can check range for individual companies. After you produce this one, you can just select, let's say, companies 2 and range salaries 2, just selection from here. And then we can say for company C, the range is 272K. It's here. So we just select this value, range salaries 2. Quantiles. Quantiles are the percentages, as you know. Here we calculate quantiles. What we need, first of all, the first quantile is the 25%. The second quantile is the 50%. This is, in fact, 50, but the same thing. This is 75% quantiles. And then data frame quantiles, we just submit an array here or list. With this list, we get 3 values for each company. These are the companies, and then this is the first quantile, second quantile, and the third quantile. Let's say, when you look at the 50th quant or the second quantile or 50th percentile, you see these are the medians of the companies. In this company, the median or 50th percentile or the second quantile is the 69K. Okay. Interquartile range, when you produce this information or this data frame, this is the first quantile, this is the third quantile. When you subtract this column from this column, you will get automatically, you see, we select this one, and then we select the second one, minus, and then we get the interquartile range for our data frame or for our data. Here in company ABC, these are the interquartile ranges, 20,000 or 20K, 32K, and 61K between first quantile and this third quantile. Is median equal to 50th percentile? Here, as I said, this is the 50th percentile, but we have, it's not indicated here, we have, let's say, calculated means above here we already calculated means. Now we just want to check, these are the means, but are these means really equal to 50th percentile? So we are just doing that here. Let me take this. We just make a comparison. If these values, I mean the 50th percentile values, are equal to the company median values calculated before, yes, they are true. As you see, they are equal to the, I mean, the median is in fact means the 50th percentile. That's the, say, the median means the 50th percentile. That means 50% of your data is below the mean and 50% of data are above the median. Again, box plots, but this time we plot our data with Seaborn. You see the dispersion, and then standard deviation and variance. It's again in pandas, or Python, very simple. When you have data frame, var is for calculating the variance. These are the variances. But here, what I already mentioned, our salaries are about the Ks, let's say 70K, 100K, or 115K. But when you look at the variance, variant is K square. So these are really bigger values. It's not very comparable to our original data. So these are good, but it's not very practical for our purposes. So we take the standard deviation of these variances. When you take standard deviation, in fact, is the square root of these values. When we produce variances, we can take the square root of this, or we can just say standard deviation. Automatically, we can get standard deviation of the data. Here you see, when we compare these numbers, company A 200, let's say 19, doesn't give you much information. How spread is your data? But when you look at this is the standard deviation of company A. You know the average is around 70K, and the dispersion or the standard deviation is something 15, around 15. This gives a much clear understanding about your data. And these are the other companies' standard deviations. That means, let's say, when you know 70K is the average of your salaries in this company, and then plus and minus standard deviation, you get 68% of people are in this vicinity. Average plus minus this standard deviation, you get 68% data points in that vicinity. Our standard deviations, similar to what we intended at the beginning. First of all, when we produced, we intended this one, 15, standard deviation 25 and 45, and then we manufactured our data, and then we calculated standard deviations. Since these are manufactured data, it's not exactly the same, but very similar to what we intended at the beginning. Here only at this company, it's a little differentiated from what we intended. Because of this number is too big, data is also dispersed. After we saw those details separately, in fact, we can get a summary statistics, data frame, describe method, and then we get this very detailed statistics, company ABC, and then how many data points, 1,000, and then these are the means, standard deviation, minimum, maximum, and then these are the quantiles. If, let's say, you don't like those details, you can round these numbers, and then you can get this kind of clearer picture. We calculated everything, let's say these quantiles separately, one by one, but here when you summary statistics with just one command, describe, you can get this kind of summary statistics, and then you can get medians from, this is a data frame, let's say you can data frame, describe, summary statistic, and then you want to get, let's say, this row. So you just select the row name with log, and then you get this. Here, company ABC, these are the 15th percentile values. That means, in fact, the medians of the companies. Again, in this data frame, if you want to calculate interquartile range, or range, let's say, so we just need the maximum and minimum values. So data frame describe summary statistics, we get the maximum values. Again, data frame describe and minimum, this row and this row with minus, we get the range for company ABC. For interquartile range, again, you have this 25 percentile and 75 percentile, first quantile or third quantile, you just select this row and this row, and then you get easily the interquartile range in your calculations. We did this above, but this is another way of doing, just to show you. These scores, as you know, these scores are calculated for all individual data points. First of all, we measure the average of data, but then if you want to care for all individual data points, how far those individuals from the average, then you have to calculate the z-scores. Z-scores is very simple, you know. You have the data points, and then you have the average of data. You just subtract the average from the data. You get the distance from the average, and then you divide that distance to the standard deviation. That means you give the z-score. Z-score is just how many times far from the average. If that data, let's say z-score is 1, that means the data is 1 standard deviation far from the average in the positive direction. If it is -2, that means the data, that individual is 2 distance far from the 2 standard deviation distance far from the average in the negative side. Here we need another library. SciPy is used here. SciPy and stats is imported. Here in stats, these scores are calculated for data frame, and then we load them in another data frame, ZDF. DF is the data points data frame. ZDF is the z-scores of all individuals. And then we put them in a new data frame. The column names are taken from the company list. And then when we look at the new data frame, these are all individuals. But instead of their salaries, now we put z-scores of those salaries. When we look at the head of the new data frame, these are individuals with the lowest z-scores. That means lowest salaries. As you remember, this individual salary was 9K, but average salary was about 150K. So when you look at its z-score, it's less than minus 3.2. When I say less than, I mean minus 3.2 is less than minus 3. Okay, that means if it is when you look at it's out of minus 3, that means it's really extreme value. Even if close to minus 3, these are really extreme values. You see, these are smallest salaries, and then their these scores are really minus 3, minus 2.8, 2.75, 2.88. These scores, if you see a z-score minus and something like 2.93, those are extremely small values, far from the average. When you look at the tail of the data frame, since these are the sorted values, tail has the biggest salaries. We have 100 individuals. These are the highest salary individuals in those companies. You see these scores are either 2.5, 2.6, or 2.7. Here you see there are even bigger than 3. That means these are really far from the averages. These scores are calculated for all individuals, and then it indicates how far that individual from the average of data. So if data is close to average, z-score is something similar to 0.2, something like that. Z-scores which are bigger than -1 and smaller than 1. You know, the clusters is in the first standard deviation. The most data points are in the first standard deviation. When you remove them, that means when you get these scores which are bigger than -1 or smaller than 1, okay, if you want them, not to remove them, these are the clustering. These are the salaries in the first standard deviation from mean. As we said in the presentation, these are the 68 points of the individuals are clustering here. So since this is a data frame, we have to use, and then there are too many lines. We don't use and or kind of things, but we have to use some logical expressions here. This means and, but when you write and here, it doesn't work since it's not only one line. There are 1,000 lines. So we are, in this logical expression, we say these scores smaller than 1 and bigger than -1. This is the first standard deviation in the salary data frame. I drop the NA values because there would be too many NA values here. Okay, here. If you don't drop NA values, you see, since these extreme values are out of the first standard deviation, these would be all NaN, and then we will not see the really important part here. So I drop the NA values. When we drop them, you see the rows start from 160 here. This value is in the vicinity, but still in company B, this individual is out of the first standard deviation. So these are not included. In case of the biggest salaries in this company, all are in the included here, but these are still not included since they are out of first standard deviation. I'm sorry, I didn't notice I passed my time. Thank you very much for your listening. This is not, as I said, this is not very advanced statistics. This is just to show statistics is not that bad, not that ugly. It's really useful and it's really used in daily life. And as I said, in the case of mean or average, it's the base form or the simplest form. But even when you go to machine learning, logistic regression, or even in the deep learning, it's kind of, you first generate an average or a line close to your data points, or a line or plane separating your plus and minus values or categories, and then you calculate these scores or each of your data points, and you calculate the distance of all individuals to the line or the plane, and then you make your calculations. At the end, you produce a model in your machine learning or in your deep learning. So this is just the introduction to descriptive statistics. And thank you for your listening. I couldn't check your questions recently. I don't know if you have any. What does figure size 8.8 and It's here, figure size 88 means you can change it here, let's say 12. You don't need this much bigger figure size. 88 is something good for me, but if you prefer, let's say, you can even try 6 and then you can get this. By the way, I want to give this notebook to Magnimind, and then I guess they can maybe share this notebook with you. It's not really something very important. It's just to show you, you can use these kind of things in your exploratory analysis, and then you can see your data, something like this. You can discover your outliers in your data. Okay. So thank you again for your listening. From Magnimind Academy. Mr. Baday. Okay, let me see here. If there is no question, again, thank you for your listening. I think we can end our presentation. I really appreciate your listening till end of the presentation. Thank you. Okay.